Up until this point in the class, we've mainly been looking at DC signals and DC circuits. So now we're going to start talking about time-varying signals. And so whenever we start talking about time-varying signals, we have a couple important terms, namely frequency response and our transfer function. And so let's start by defining what our frequency response is. So all our frequency response is basically if we have some signal coming into a circuit, as that frequency varies, we're going to see some variation in the behavior of the circuit. So variation of a circuit's behavior as that signal frequency is varied. And so what we're going to see here in a little bit is that we have two components of this frequency response. We have a gain component, and we also have a phase component. And so both are going to be important depending on what we're looking at. And so let me just mention now too that these are topics that you're going to see in other courses, and maybe you are seeing in other courses, so FE&G 301, control systems in the spring semester. So these concepts kind of are running through various courses. So in order to talk about this idea of a transfer function more clearly, what we're going to do is we're going to consider some linear network. And so this is kind of going to be how at the start of circuit analysis we say, let's just consider some general element before we even introduce resistors. So here we're just saying let's consider some general network. And so this is our linear network here. And so a linear network can be characterized by something called a transfer function, which is h of s. So h of s is defined as our transfer function. And so that is going to completely define the system. And so again, we'll come back and we'll talk about transfer functions a lot in control systems. So if we have some input into this linear network, so let's say we have some input capital X of S. And so what we could do is, knowing this transfer function of the linear network, which we could, let's say we know how to determine that, we'll learn that in future classes. And for any given input X of S, we could then determine what our output Y of S is. So I'm going to do capital Y of S. Okay, and so where X of S over here on the left, so this is just going to be some phasor input. And so that could be either a voltage or a current. And then Y of S over here on the right is some phasor output. And so again, that can be either a voltage or a current. So again, I'm throwing around a lot of these terms. So if you're unfamiliar with the terminology or anything that we're going over, feel free to send me an email or let me know if you have a question. So again, these phasors, just like with our frequency response, we're going to see that they have relevant magnitude and phase information. So let me make one more note before we move on too. So you notice I have this, all of these are functions of S as opposed to functions of time. So of course we're talking about things in the frequency domain, and recall that our S is defined as j omega. So our omega is of course where we get our frequency information from. So remember, omega is 2 pi f. And then our j is square root of -1. So this is our imaginary number. And so oftentimes in other classes, particularly math classes, you'll see the j, instead of j we'll use I, but of course in electrical engineering we already use I for current, so to avoid confusion we use j. Okay, so now coming back to this linear network. So this h of s is actually going to dictate the relationship between that input and output. So for a certain input x, we get an output y. And so we can write that then as a ratio of the output to the input, like such. And so we know that our transfer function is going to be a complex value. So it's going to have some magnitude, which I can write like this. So sort of the absolute value, it looks the same as that. So that's our magnitude of h of s. And then angle with some phase angle. So this is sort of the definition of our transfer function. And so again, note this is a complex value. And that complex value consists of our magnitude and our phase information. And so we'll look at an example in the next video, because I know a lot of this stuff kind of is hard to grasp without an example. So if we just put in some numbers, for instance, if we're talking about maybe a sinusoidal voltage or sinusoidal current signal, we have something that looks like that based on the phase shift phi. So we'll have some magnitude, so maybe we have a magnitude of 120, and that's at an angle of 30 degrees. So this is what something like this would actually look like if we had some numbers to plug in there. So we can represent this transfer function with a couple different general forms. So we're going to look at one now, and then we're going to look at a separate general form a little later on. Of course, they both represent the same things, but they each have their own sort of ways to help us understand different parts of our transfer function better. So in this first general expression for the transfer function, we can write this as h of s is equal to k times n of s divided by d of s. And so this k is just a constant value. And then we have some numerator polynomial, which is a function of s, n of s, and a denominator polynomial, d of s, which is a function of frequency as well. So I can write this, expand this a little further. So we still have our constant k, and then let's expand this numerator polynomial and denominator polynomial a little more. So for our numerator polynomial, we can write this as s minus z1 times s minus z2 times so on and so forth until we get to s minus z sub m. Similar thing for our denominator polynomial. We can write s minus p1 times s minus p2 dot 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 times s minus p sub n. So each of these z's up here, so our z1, z2, so on all the way to zm, are the zeros of our system. So zeros of our system, or zeros of h of s. And so why do we call these zeros? Well, when we have s equal to any of those zeros, we can see that that makes our h of s equal to 0. Our p's, the p1, p2, up to however many p's we have, we call our poles of our system, or of h of s. And so our poles, so if we consider what happens when we have s equal to a pole value, so s equals p of I, that makes our transfer function infinite. So we have a 0 in the denominator of our transfer function. So one thing to note is that we don't necessarily have to have m equals n, so that's not needed. And so all that's saying is we don't necessarily have the same number of zeros and poles, and oftentimes we will not have the same number of zeros and poles. This is a concept we'll dig into a lot more in control systems. Okay, so that's sort of a basic introduction to our frequency response and transfer function. I know that's probably just confused you more than anything, so in the next video what we're going to do is look at a simple example to kind of help grasp these concepts a little better.